Hey, so welcome back, and we're going to do some more LeetCode problems. So today what we're going to do is continue on with this Blind75 list of questions. And so we're going to work through these linked list problems. And so I'll add this website in the description. It's LeetCode.io and it's free to use. And so essentially, what this list is, if you don't know, it's basically a bunch of LeetCode problems that a few FANG engineers put together as to what problems are the ones that really teach you the best lessons and that you'll really benefit from doing. And so they're organized by different categories of different problem patterns that you might work with, as well as different data structures that you might have to interact with. And so today we're going to do the linked list problems associated with this list. All right, so let's get to it. So the first one here is we're given a linked list, and all that we want to do is reverse it. And so what that means is it goes from like 1, 2, 3, 4, 5. We want to make it 5, 4, 3, 2, 1, right? We want to reverse it. And so for me, the best way of thinking about this isn't really like, let's put 5 over here and let's put 1 over here and say 4 there. What we really want to do is actually just change the direction of these arrows. So we want 2 to point to 1, 3 to point to 2, and continue on here. 4 to point to 3, and then 5 to 4. And basically, we're just going to return this as the new head of our linked list. All right, and so that basically created this linked list here. So to do that, we essentially just want to keep track of 3 different things: the previous node, the current node, and the next node. And this is pretty common for a lot of these linked in problems, or linked list problems, sorry. And so this is a great thing to keep in mind. And so essentially what that's going to look at is, okay, what about this first case? So this would be our current node here, but what about our previous node? Well, for that we'll just say null or nothing at first, because, well, what comes before it? Nothing. And then the next node, well, of course, that'll be this one here, number 2. And so what this will look like is, say this is our current node, and this is our next one, and then this one's our previous. Right? And so essentially to change the direction of this arrow here, which is what we would want to do at this step, all that you have to say is current.next is going to equal to the previous node. Okay, so that's basically going to be changing the direction of this arrow to point to the previous one. But from here, in order to kind of move forward and then do the next one, we have to kind of maintain these 3 different pointers. So to do that, we just have to say, okay, the previous is now the current, and then our current is now the next one. So that just allows us to move all of these 3 pointers forward along this linked list, and then keep kind of repeating this step of reversing the direction of that arrow. All right, so I think that's enough explanation. Let's go ahead and do some coding. So essentially, what we want to do, once again, is keep track of the previous and the current node. And so initially, nothing comes before the current node, and we're going to start at the head of the linked list, or really the first node. And so we want to say, okay, while we still have a node that we can work with, right? So while this is still not null, or we haven't hit the end of the linked list, let's go ahead and reverse the direction. So what that would be is, okay, the current.next is equal to the previous, right? So that was that first thing I showed you of changing the direction to now point to the previous node. But in order for us to keep doing this, we have to keep track of what the next node is. And so to do that, we can just say, before we update it, let's say that the next node is current.next. And it's important to do this before we update it, because, well, if we do this afterwards, well, it's always going to be the previous node here. So let's put it here. And so from here, we just have to kind of move forward and maintain these 3 pointers that we have. And so to do that, we just have to say, okay, well, our previous node is now the current node. And then our current node is now going to be the next node. So next.next. Right? And so at the end of this, once we hit the end of the linked list, we're going to expect current to be null. Right? So we're going to hit it all the way until our current node points to nothing. And so that will happen basically at the very end here. So our current will be here. This will be our current node, which is basically nothing. But our previous pointer will be pointing here. And so because this will be the new head of our linked list, we want to return this one. So let's return our previous node. And so once again, let's go ahead and we just return previous. So let's go ahead and run that. Oh, sorry about that. So basically we can't use next as a variable name just because it's a special word or variable. And so we'll just say that this is next without the E. Sorry about that. Great. Has no attribute next. So next is equal to current.next. So our current will be equal to the next one, sorry. Yeah. Great, and so that's the first one. Sorry about that little mix up there. So you don't want to say next.next. You want the current one to be equal to the next one, not the next one. All right, so that's the first problem here. So let's move on to the second one, which is merge two sorted lists. And so for this problem, we're just given two sorted linked lists, and we want to basically return it as one list. So we're basically merging these two lists here as one. But they've already helped us a little bit because they're both individually sorted. So to merge them, we want to maintain that kind of sorted order. So to do that, we'll basically have two pointers, one pointing to the first list and one pointing to the second. And so we'll use another common pattern where essentially we'll have like a dummy node, and it's literally called, most people call it like a dummy node. And so what this is used for is just to create our third list, which we're going to use to basically build this one. So rather than trying to like insert one of the lists into the other, we're just going to create a new list and just attach these nodes to it. And so essentially we'll say, okay, which one is smaller? Well, they're equal to the same, so we can just grab either or. So let's go ahead and add this one. And then we'll compare these two, right? So we'll move this pointer over to this one now. We'll say which one's smaller, this one. So let's add that to our list. So now we have 1, 1. And then we compare, okay, 2 or 3. Let's add 2. And then 3 and 4, let's add 3. And then basically it goes 4 and then 4. And then this is our new linked list. But once again, we don't want to return -1 here. We'll want to return this 1 here, which is really at the beginning. This is just a dummy node we used to basically create this list. And so to do that, we just say, okay, let's return dummy node.next, right? So the next one after this dummy node. All right, so if this doesn't make much sense, let's go ahead and look at the code, and I think it'll help a little bit. All right, so essentially, once again, we want to have some dummy node, and let's create that node using this linked list class that LeetCode provides to us here. And so with this, we want to return basically dummy node.next. But this will just be used so that we can basically populate and create this new linked list that we're building. And so we want to say, okay, while list 1 has a node, or list 2. And I think just for better explanation, let's just call this like node 1 and node 2. Right, so we're just comparing these two nodes here. So while we have either or of them, and so at least one of them hasn't hit the end, let's kind of continue generating this new list. And so we can say, okay, if we have a node 1 and this node has a value that's less than the other node's value, then let's basically, since we want to have the smaller one, let's basically add that to our list. And so to do that, we basically want to keep track of what's the current last node in our list, because we want to be appending to the end. And so we'll just have a kind of current node here that's initially pointing to our dummy node. And we'll just say, okay, current.next will be equal to this new node. And then because we want to kind of keep moving forward from here, because we just used node 1, we want to use the next one in that list, we'll just say, okay, node 1 is now equal to the next one, right? Because we can't use this one again, so we want to move this one forward in its list. Otherwise, if this is not the case, then that means that node 2 is actually the smaller one. And so in that case, we basically want to repeat this logic, but be using the second list instead. Awesome. And so from here, there's one other thing that we'll have to keep track of, and that's the case where, okay, what if node 2 is actually empty? Because we checked for node 1 being populated, but what about node 2? And so if that's the case, well, if node 2 is empty, then node 1 will not be empty, because either one of them has to be non-empty, so it would be this one. And so this will pass this check, and then it will grab the node's value. But here it'll throw an error because we can't do null.val. And so basically we have to check this and try to prevent that. So if node 2, or if not node 2, so if this doesn't exist, or this case here, right? And so that just prevents this from throwing an error if this is actually null. So let's go ahead and try running that. Oh, looks like we have an error here. So what we're missing is basically a bunch of stuff. So let's see what's wrong. Dummy node.next. So we're saying current.next. So the reason behind this is we're not moving forward from our current. We're never saying, okay, we just added a node. Let's then set the new current to that new node we added. So we have to do that with each iteration. And so we just say current is now the one that we just added last iteration. Great. And success. So that's the problem here. So let's go ahead and do the next one. So this one's called Reorder List, and it's a medium level problem here. And so essentially what we're given is we're given one linked list, and we want to change the ordering in which it comes. And this is a really challenging problem. I think this one should be a hard level one, and then the hard level one should be like a medium. But let's go ahead and implement it. And so essentially what we want to do is you want to reorder this list so that first it's the first node in our list, then it's the last node in our list, right? So it goes 1, and then 4, and then it goes second node in our list, which is 2, and then we want basically the second last node in our list, which is 3. So it's basically like 2 pointers that are kind of moving forward and generating a new list again. And so to do this, essentially, we're going to use that dummy node technique once again, where this will be just some arbitrary node used to build a new linked list. And we'll want to have those 2 pointers again, right? So they're kind of moving forward and meeting in the middle. But the challenge here is that this is a singly linked list and not a doubly linked list. And so we don't actually have pointers pointing backwards. So there's no way for this pointer to then move inwards. And so to fix this, what we'll do is actually reverse the second half of the linked list so that we are basically pointing these pointers in the opposite direction. And so essentially, in order to implement that, we just have to grab this blueprint code that we made in the reverse linked list problem and implement it here in the medium problem as like a sub problem that we have to do to solve this. The other catch here is that we only want to reverse the second half. And so we're basically going to do this by basically finding the middle of this list and then saying, okay, let's reverse only the second half here. And so once we reversed the second half, so this will basically point to nothing, and then this 3 will also point to nothing. And so basically cuts the list in half. And we're basically just pointing this pointer now to be pointing in the opposite direction. And so now we're actually able to have 2 pointers, pointer 1 and pointer 2, each pointing to the end. And we're able to actually, with each iteration, move them inwards. And so that allows us to say, okay, let's add the P1 here, and then let's add P2, and then let's move them in, and then we'll add P1 again, and then add P2 and move it in, and so forth. All right, so let's go ahead and implement this. So once again, we want to have some dummy node, which initially will just be -1. And so at the end of this, we're expecting to return dummy node.next. All right, so we're building a new linked list. And so our first step has to be, well, okay, let's find the middle of our linked list. So find the middle. And so the common way of doing this is something called the hare and the tortoise, so like the turtle and the rabbit. And so basically those are two pointers, P1 and P2. And so they'll initially be pointing to the current node and the next node. And so basically to find the midpoint is if you have one node that moves one node ahead each step and another node that jumps twice, then because one's going twice as fast, when you hit the middle, the one that goes half as fast, or sorry, when you hit the end, the one that goes half as fast will be at the middle, right? So if someone's twice as fast as you, when they reach the end of the finish line, you'll be halfway there. And so that's just a clever way of finding the midpoint. And so all you have to say is, okay, while we have our second pointer and there's a spot that comes after it, we can kind of continuously be moving forward. And so we just say, okay, P1 is just going to P1.next. And so P2 is basically going to hop twice here. So that's why it's called the kind of tortoise in the hare or rabbit in the turtle, is one's faster and one's slower. And so with this, now our P1 we know is going to be at the midpoint. And so all that we have to say is then, okay, let's reverse the second half. And so we'll create that. So we'll create a method here called, what do we call this? Oh, and this isn't called reverse the list, I don't think, because I deleted my code earlier. So if I reset this, just one second. Yeah, it's called reorder list. So let's go ahead and I'll paste it again. And we're going to create that method called reverse list here. And so it's going to be needing the current node. So let's just pass in the node here. And so we essentially just want to call this method here. And so we just say, okay, let's reverse our list the second half. So because P1's our midpoint, let's go ahead and return the node that comes after this midpoint. And so after we do that, we want to basically set our P1.next equal to none. And so that just allows us so that, okay, we're going to reverse this second half here, but we no longer want this 2 to point to 3, we want to point it to nothing. And so let's just go ahead and do that. All right, and so from here, let's go ahead and implement our reverse list. And so all that's going to be is, once again, this is kind of the other linked list problem that we did earlier, is that we want to keep track of our current, our next, and our previous. And so our previous will initially be none, and we already know our current node here. And so we just want to say, okay, while we have a node, let's keep going. And we want to keep track of our next node. And then basically we want to reverse the direction of that arrow. So our current node .next is going to be pointing to the previous one. And then let's just go ahead and update these pointers so that the previous is now the current and the current is now the next. All right, and so from here, all that we want to do is, because this will be null at the end of this, right? So while this is not null, we want to return the previous, because we don't want to return null. We want to return basically the new head, which is the previous. All right, and so now that we've reversed our linked list and we set the other list to now point to null at the very end, and this was basically step 2, was reversed list. From here, all that we want to do is then say, okay, now that we just reversed this list, we want to, and just let me think for a second, we want to move them forward and build this new linked list that we're generating here. And so let's build the new list. And so to do that, we just want to say, okay, let me think. I think it's that, okay, while we have our P1 or our P2. And so if that's the case, well, how do we know whether we want to add P1 or P2? And so the way we know this is just by, I believe, just alternating through them. Yeah, so first we do the left side, then the right, then the left side, then the right, and so forth. And so to do that, essentially, all that we want to keep track of is first we want to add the left side, then the right side, then the left side, then the right side. And so to do that, we just want to say, okay, what's our current count? Well, initially at 0. And so if the count, the mod of it, is 0, then we know it's an even number. And so let's add the left side. When it's an odd number, we'll add the right side, and this just allows us to alternate between the two. And so if it's an even number, then we're going to want to say, okay, let's add what's at P1. And so to do that, we just say, okay, well, let me just think here. We'll do our current and we'll add to it. So to do that, we just have to update where our current is. And so we'll say, okay, our current node will initially be pointing to the dummy node and we'll want to add to it. And so from here, we'll just say, okay, current.next will then be P1. And then naturally, because we just used P1, we want to move forward from there. So now we'll update it to now be pointing to the next node in that list. Otherwise, we want to do basically the reverse of this. So let's yank it and put it here. And so instead we want to use P2 and we'll basically want to increment that as well. So let's try running this. Oh, so node does not exist. And so that's because, well, we haven't set it yet. So basically node will be equal to the head. And not defined, well, we have to call self in order to use that. And current hasn't been referenced before. Oh, so I'm calling it current, but it should be called node. Node. Has no attribute next. So this is saying, okay, while P1 or P2, but P1 does not exist. Let me think here. So can these vary in length? So I'll just say, okay, if P1 and then else if P2, then we'll keep going. Oh, and so from here, we also want to be keeping track of and incrementing the count with each iteration. And I believe else we don't need this anymore. So that's hitting that error again. So the count modded by 2, if that's 0. So if P1 and, what happens there? Let's take a peek. So we'll have that. So it's not alternating, it seems like. Okay, because I don't want to waste too much time just doing this live, I'll just go ahead and just compare what I previously implemented, just so I'm not wasting too much of your guys' time. So essentially, we'll just paste this here and see what the difference is. And so, while I'm doing this in real time, let's just see here. So we don't need this. So let's take a peek at the reverse list part. That should be fine. So are we reversing the same? So previous none, while the next equals that, node.next is that, previous, and we swap it, that looks good. Then from here, we want to say, okay, our dummy node is that. And then our P1 and P2. Looks good. And so from here we want to reverse the second half, which we do, and we set the next one to null. And so we want to say let's meet in the middle. So while P1 or P2, which is what we're doing, we have our P1 pointing to our dummy node, and our current node. Oh, I see. So we have to reset our P1 back to the head. Yeah, that's something that we missed. So let's set our P1 back to the head node because right now it's at the end of that first list there. So let's go ahead and just delete this node and try running that. Oh, looks like we have the same error. So P1 is set back to the head. We use our dummy node for the current. So while we have either or, that all looks good. Oh, I don't know what I did wrong there. I think I just compiled it with the other code. So basically the only thing that was missing was that, okay, naturally, because we used P1 here to find the middle of the node, and we're basically passing it here as the next will be null, this was being set still as the end of the first half. And so we just want to set our P1 back to the start of the linked list. Sorry about that. All right, so let's go ahead and do the next one. And so I think we'll skip ahead just for me to have a break, because we'll do this easy one, then we'll do the next medium one. So this one's called a linked list cycle, and essentially we just want to return true if there's a cycle and false otherwise. And then all that a cycle is just an arrow that points back to a node that can kind of get to the current node. And so because of that, it causes an infinite loop. So to do this, there's kind of two different ways, and one's better. One way is you can have a set, and you'll just add to this set whenever you visited a node. So if you visited 3, we'll add that node. Then we visited 2, 0, and then 4, right? So as we're iterating along here, we add this to our set. But once we reverse back here, we'll basically say, okay, is this node in our set? And if it is, and in this case it is, it's right here, then let's go ahead and return true because we already visited this node. And so if we've gone back to it, there must be a cycle. Otherwise, if we reach the end of the linked list and we never see that the node we're visiting has already been visited, then we'll want to return false and basically say there was no cycle. All right, so that's one way. But the better way is basically using something called, once again, the rabbit and the hare. And so basically you'll have 2 pointers, one going basically 1 hop every iteration, and then the other one's going to hop twice every iteration. And so the idea behind this is basically you're going to start one of them like so. So it's going to be hopping just once from the beginning. But the one that hops twice as fast, you're going to set it at the first position rather than both of them starting at the beginning here. And so because of this slight modification, eventually what you'll expect is that the turtle will end up on the same node as the one that goes twice as fast. And once this happens, once you see that, okay, they're on the same node, the only way for that to happen is that they've iterated enough for that turtle to basically be at the same position as it. And it's basically like a mathematical fact that, okay, if one's going twice as fast and one's going half as fast, eventually, if there's a cycle, they'll meet at the same place. All right, so let's go ahead and implement that. And the reason why it's better is that it's basically still O of n time complexity, but basically it's O of 1 space complexity. And that's because we're just iterating and we don't have to use a set to find out if we visited it before. All right, so to do this, we basically want to say, okay, we'll have 2 pointers. and one's going to start at the head, and one's going to start after the head. And we're going to want to return false if we never find a cycle. But let's try to find a cycle. And so to do that, we just want to say, okay, while we have a P2 and a P2.next. This is just kind of blueprint code that we typically write for these like two-pointer, they call it rabbit in the hair problems, where one's going half as fast and one's going twice as fast. And so one's going to basically, once again, move one step every iteration, and one's going to move 2 steps. And so we'll just want to return true if they both land at the same place. And so that means that there must have been a cycle such that it allows the one that's going half as fast to eventually be at the same place as the one going twice as fast. All right. Let's just see what I did wrong here. So, this happens where, okay, if head is empty, then we'll not be able to do head.next. And so we just want to account for this special case of saying, okay, if there is not a head, then let's return false. And so if they're just giving us an empty node, then let's just return false, because having an empty node will obviously never have a cycle. Awesome. And so from here, let's go ahead and do the medium level one called remove nth node from end of list. And looks like I forgot to erase this one from this morning. So let's go ahead and do this one. So essentially, what we're given here is a linked list, and we want to return the nth node from the end of the list. And so all that means is that if we want to return the second one from the end, that would be this one here. And so if n is 1, then we're essentially trying to remove this one from the end of the list. Okay, so let's go ahead and do this. So essentially, the first thing that we'll want to know is what is the length. And so that allows us to know, okay, if the length is, say, 5, if we want to remove this one, we'll essentially want to iterate up to like this point here, and then basically remove it. And so we'll iterate basically all the way up to 5 minus 2, which is, I guess, 3, but it's really 3 minus 1, I guess. So it's really the length minus the number that's given to us, which is 2, minus 1, just because it's 0 indexed. And so that allows us to know, okay, let's iterate all the way up to this point, and then basically hop over it and point to the next thing over that node. All right, and so to get the length, you just basically keep iterating until you hit the very end. You just have a counter counting the nodes. And yeah, I think that's mostly the algorithm. So let's go ahead and implement it. So essentially, the first thing that we want to do is find the length. And so let's keep iterating while we have a node. So we're going to start at the very beginning, and we'll have some integer representing the current length of the list. And so with each iteration, we're just moving one step forward, and we're just incrementing the length of the list. All right, so what we'll find at the end of this is, okay, the length will carry what is the total length of the list. And so from here, we'll basically want to iterate just up to right before the nth node from the end of the list. Okay, so essentially if we want to remove 4 here, let's iterate all the way up to this one here, and we'll basically remove it by setting this pointer to point to 5 instead. Okay, but first let's iterate up to that node number 3. And so to do that, we just say, okay, for I in the range of basically the length of the list minus n. And we don't have to do minus 1 here because that just happens implicitly using this range function. All right, and so from here, we just want to say, okay, this is how we iterate all the way up to that nth node. So let's go ahead and do that. So we'll basically set our node back to the head of the list. And with each iteration, we're just kind to move one step forward here. Great. And so now we've iterated all the way up to just before the node that we want to remove. And so there's a couple edge cases that we'll have to worry about here. And so the first one is that, okay, what if we're trying to remove this node, right? So this is the head. And so to remove that node, all you have to do is basically set the head to the next one. Okay, so let's say that, okay, if the node is basically the head, then let's just return head.next, or really node.next. Okay, so that's the first case. The next one is, okay, what if we're, let's say at this one here, right? So what if we're trying to return or remove the very last node here? And so essentially we want to return this node and just set the next one to null. And so that's a challenge here because this will be the current node that we're trying to remove. And so we need to keep track of what comes before it so we can set what its next thing to as null. Okay, and so to do that, we'll basically have to include previous in this iteration. And so essentially at the beginning, previous will be nothing, so it'll be none. And we're going to want to repeat this where, okay, with each iteration, the previous node will be the current node, and then the current node will now be the next node. Okay, so otherwise, if the node dot next is nothing, then it's the tail. So this accounts for what if the node is the head. This accounts for what if the node is the tail. And so to handle this case, we just say, okay, then the previous node dot next will now be nothing. And so we're just removing the tail essentially and setting the new tail as the previous node. Then otherwise, we'll just want to do a standard removal, and we'll just say, okay, then our previous dot next will be our current dot next. Great, and so from here, all that you want to do is return the head of the list. Let's try submitting. And success. So this runs in O of n time complexity because we're just essentially iterating through until the end of the list once. And then the space complexity is O of 1 because we're not using any extra data structure other than just pointing to the linked list. And so yeah, we're just going to do the final one, which is the hard level problem here called merge k sorted lists. It's a hard level difficulty one, but I find it much simpler than this one and maybe some of the others, because like some of these have tricks to them and there's no way we would be able to figure it out on our first attempt. But once you know a few of these tricks, you get to reapply them to other problems like this or other ones. So essentially for this, what you're given is actually an array of linked lists. And so they don't really represent it very well here, or I guess they show it here better. And so it's basically an array, and inside this array is like multiple linked lists. Like so. Okay, and so what we want to do is basically merge these linked lists, this list of linked lists, into just one. Okay, and so the benefit of this is that we see here they're already kind of in sorted order, and we want to merge them into just one sorted list. So it's very similar to merge two sorted lists here, except now it's k sorted lists, or it's a list of lists. And so you're not just dealing with two, you're dealing with basically as many as possible. Like it could scale to being 2 lists, 1 list, or 20,000 lists, all right? And so to do this, essentially what you need to think of is to use a heap. There's other ways that you can do this, but I found heap was the simplest, and it's what I thought of when I was implementing this. And so essentially, by using a heap, you can essentially keep track of what is the next node that you want to use, because with a min heap, you're allowed to kind of quickly and O of 1 time complexity grab what is the next smallest number. That's what heaps are for. Like at the top of the heap will always be the smallest number available. And so by pushing to a heap with all these numbers, we can just basically pop from it as we're building our new list so that we can have in ascending order our new sorted list. Okay, so we're just iterating through these linked lists here and all their values, and we're just pushing to a min heap. And so to build our list, once we have that total min heap with all of those nodes, we just pop from it with each iteration and generate our new list. Okay, so I hope that clarifies a few things, and I'll show you the code, and I think it will help a lot too. So let's go ahead and implement this. So essentially, we're going to first have our min heap. And so it's essentially just an array in Python initially. And we're expecting to return some newly generated list. And so whenever you hear this, you should instantly think to use a dummy node. And so we're going to return the dummy node.next. And this is what we did in the previous problem. So if you haven't seen those, I'll tell you to look ahead because this is a common pattern that we used before. And so essentially, we just create a new list node with some just random value associated with it, just so that we can create a new linked list. All right, and so from here, the first thing we want to do is push all of the linked list nodes to a min heap. And so to do that, we just want to iterate through for every single linked list in our list. So for every node in lists, let's go ahead and iterate through them. So while we have something still on that particular linked list, we'll be essentially moving forward. So we're going from left to right to the end of the linked list for each one of them. And we're just going to want to be pushing that node to our min heap here. So to do that, we just use heapq.heap push, and we'll basically want to push to our min heap the value of that node. Great, and so after this, we've pushed all of the linked lists and all of their nodes associated with them to our min heap. And so from here, we'll just want to say, okay, while we have something on our heap, so while min heap, we'll want to pop from our min heap and add to our new linked list. So let's pop all of the nodes off and add them to our list, basically in sorted order. Awesome. And so from here, we'll just want to say, okay, what's the new value that we're going to be adding to our linked list? Well, or really our new node here, new node. And so that will basically be whatever we're popping off our min heap here, heap pop. And so we're just popping off of our min heap. And so to convert this from a value into a list node, we just do it like so. We just use our list node class. And so from here, well, how do we keep moving forward? Well, we keep doing this while we still have something on our min heap. So with each iteration, we're popping, we're creating a new node. And so how do we actually add that to our linked list? Because currently we're just popping. Well, we want to say, we want to keep track of our linked list, but then also the end of it, because we want to keep adding to the end. And so basically we'll say our current node will initially be the dummy node, but with each iteration, we're basically adding and appending to this list that new node. That new node, great. And so from here, the only thing that we'll want to update is our new end of the list. So if you added a new node, then now the end of the list will now be that new node that you added. So then our current will now be current.next. So let's try running that. Looks good. And success. So for time complexity, it's essentially going to be, I think it's like k log n, and that's the time to basically push all of the nodes to our min heap in sorted order. So that's a time complexity of basically heapifying all of these nodes. And then from here, our space complexity will essentially just be the number of nodes in all of those linked lists inside of them, because at worst case, this min heap will be holding all of those nodes. All right, so that's the end of the Blind75 lists and the associated linked list problems with them. Next time I'll be doing the tree problems, probably today, or probably not today, probably tomorrow or the next day, but it will be a long video of 11 problems. So yeah, I hope this helped a little bit. I think this teaches you a lot about how to manipulate linked lists, some tricks associated with them, like using a dummy node whenever you're generating a new linked list, or reversing lists, or merging them together. So these are common things that you have to do and different tricks that you need to have in your belt when you're solving these problems. So super valuable thing to work with. And yeah, thanks for watching and good luck with the rest of your algorithms. Great, see you later.